Thanks for joining, y'all. Putting this wide angle lens so I can stream TikTok. And we'll get started. Yep, I think that's working. Cool. Dawn just joined. What's up, Dawn? Cool. So in front of us, we can see an article on forward feature selection. The issue is that I have a bunch of variables and I don't have enough samples, so I can't use backward selection as I would prefer. Let me review some of the things that I've done. Hey, I'm pretty good, man. Thanks for asking. Oh, I should also open up the Twitch chat in case anyone on Twitch wants to say hi. Doing more data analysis today. Still working on a gender research paper that I'll be presenting in November next month. So here's some of the things that I've done since the last stream. Here's the variable definitions file. I compute a bunch of variables. This is an exploratory file. I think we've done that together. Factor groups. I believe I streamed when we determined that the comparative skill gap is useful. Well, slightly useful, not really, huh? But using the no relative overqualification pattern is preferable. So here's something that I know that I haven't done on a stream before, which is leave one out cross-validation, LOOCV. So I was trying to do I think like an elastic net or a lasso. So elastic net is preferred, and then lasso is like, well, if you can't do an elastic net, maybe try lasso. Although ridge regression would be arguably better than that. So lasso is problematic because it's an unstable feature selector. What does unstable mean? Say there are two variables that are basically collinear. So say that they're perfectly collinear, 50-50 split. Lasso, it's not deterministic which one it'll pick. It could just pick either one. And so a ridge regression would say, hey, both of these are like about equally strong. And a lasso would just drop one and keep one. And if you like resample, and the variance in those factors changes by like 1%, it'll select the other one. So that's why we say it's not stable, it's unstable, it's not reliable. So it's fine for like machine learning when you care about prediction, because from a predictive standpoint, if you're just trying to minimize like error, like mean square error or whatever, you can take either one of those because they're collinear, right? So either one of those represents the same predictive capability. But what I'm doing is feature selection, like theoretical analysis and hypothesis testing. So I really don't want to do that because I don't want to drop the wrong one. Because what if one of the factors is related to my hypothesis and then one isn't, and like it unexpectedly keeps the other one. I have no I don't want that to happen. So I would prefer an elastic net or a ridge regression if I can't get a net to work. But the good news is I got a net to work. I tried to do a test train split and I got a negative R squared, and the R squared was so bad it was less than -1, which I'm still baffled that that's even possible. But basically the explanation I was given by some statisticians through Stack Exchange is that like I don't have enough samples and I shouldn't be doing a test train split basically. So instead of doing test train split or k-fold cross validation, which is like the higher level of robustness validation, instead of doing that, I did leave one out cross validation, which what that does, say I have 80 samples, it will drop the first sample, test, restore the first sample, drop the second sample, test, restore the second sample, drop the third sample, and it'll go loop through all 80 samples, dropping one at a time, and then kind of average across those. And it's another way to do cross validation. It's, hey, what's up, cool kid? So I'm doing a data analysis in Python today. Talking about data analysis in Python. Leave one out, cross validation. Oh, I guess the screen's a little blurry. Let me try and fix this lens. It says, it should say elastic net on line 116. Yeah, now you can see it better, right? Elastic net on line 116. Yeah, so like I got that working basically. And so here are, with the elastic net, you tune it using a couple hyperparameters. One is called the L1 ratio, and the other is the alpha parameter. But because I'm doing cross validation, I can optimize the alpha parameter in an unsupervised way, which is ideal. So I really only manually calibrated the L1 ratio, and I tested all of these. I would like to have tested 0, but it's actually not supported. But I got arbitrarily close to 0, and I got close enough that I'm happy, because what I was kind of wondering is, hey, is gender even in the top like 50% of factors, right? And the answer is yes. So what is the total count? Count non-zero. I didn't write it down there. If I run the script, it'll count it for me. It's like 200 something. Oh, 165 variables before filtering. No, that's not right, because here's 187. Yeah, I think there's 165 in the non-interacted. Yeah, that's just copied and pasted. 165 variables before any filtering. Let's run this. Rerun number 6. That's gonna crash. Okay. How many viewers do you have? I actually don't know. Maybe 3 or 4 or something that I can see. Okay, so let's comment this line. That's the one that's erroring. Run this again. Kitchen sink total variable count is 246. So I'm going to write that down. So, 246 variables before any filtering. So leave one out cross validation is what I was doing. And basically gender ends up being in the top 78 out of 165 variables. And it's somewhere between 34 and 78. I don't know. I could test like .03. You know what? Let's even test that. So the L1 ratio is currently 0.03. Thanks. See you, cool kid. Okay, so we're going to run analysis 4. And what we've done here on line 156 is we changed the L1 ratio to be 0.03 so that we can get a more precise boundary on the percentile of importance of gender. I kind of don't care because this is plain gender, and I don't really think plain gender is very useful. It's interacted gender that's really useful, but like maybe this is still going to be helpful. Okay, so 42, and there's no gender variable, and 0.40 is the R squared. This doesn't seem right. Oh yeah, it does. 42. let's make it 0.05 because I should not be getting more than the .05 boundary. So .03, let's change it to .05 and see if I can even reproduce what I previously said. Okay, so I did an L1 ratio of .05, and we got 34 variables, yep, with an R squared of .4129 round to .41. So that's accurate. So we reproduced .05. Now let's go to .03. I should get fewer, not more. Oh, I guess I don't care about that though, because I want to know nope, that's right. I should get more. Sorry, blanking. I put it in the wrong order. .1, .05, .03. So we're getting smaller and smaller. So let's do it again, but I think this is right. So .03. The smaller penalty will basically, so this is, the L1 ratio is basically the penalty. So the smaller penalty will permit more variables to be retained. So here's 42, great, 40, yeah, 398 rounds to 40, and gender, and there's no gender variables here. And let's go for 02, why not? Let's try and find more precisely, where is gender dropped? 02. Because we can see that gender exists in the top 78 and it doesn't exist in the top 42, and we just want a slightly more precise understanding of where it's dropped. So R squared 397 still rounds to 40, but now we have 51, right? And gender is still not here. So it's kind of looking like .01 is where it happens. And so that's okay, right? There was kind of a big gap between 34 and 78. It's like more than 100% gap, right? So good that we kind of interrogated that gap further. And the answer is that the .01 L1 ratio threshold is like where we find gender. Sure, I could find like, you know, some like strange, maybe even it's .015. Like I don't really care. I think this is good enough because what we can say is that it's in the top half. 78 out of 165 is roughly 80 out of 160. It's in the top half. If I had found that it was under 50, it'd be like, ooh, it's in the top third. That would be like slightly impressive. But if we find out that it's like, hey, it's like number 64, like, do I care? What I think if I can say it's in the top, what, 40%, is that cool? What would be 55? 55? All right, fine. I'll do this. I feel like this doesn't matter, but let's go check it out. 015. So stupid. This doesn't matter. 015. Maybe I can squeak out that it's in the top third still. Okay, 015. Let's test it. Billie Jean, how's it going? All right, so we found it in 69. Like, are we impressed? I don't know. 69. So it's not just the top 80. So what is 69 out of, I love that it's 69, by the way. What's 69 out of 165? So for like top 42%, I guess that's slightly more impressive than top 50%, but it's really like, dude, who cares? But I'll make a note. So here the note, .015 L1 ratio 69 out of See, and how annoying is it that we're at 42%, right? It'd be better if I could say 40%. So what if I was 67? Could I say that? 60, 66. Okay, so let's try. I feel like this is really like a side quest that I don't need to do. But let's go for like 0175. Blah. Okay, so 62. So we got top 62 out of 165. Cool, so we beat 40%. So, okay, that was kind of worth it. That slight nag that's like, just do it, just do it. Can we go for 018? 018. And 57. Okay, we're in there. Can we go for 019? Really pushing my luck now, huh? Oops, I interrupted it. Might be. Here's 018. I trashed that process. Oops, new terminal in research papers, alt ed gender, C papers, alt ed. Cool, so we got 57. Was that 019? I actually don't know. Is that 019? Let's run it one more time. Cool, so we pinned it pretty precisely. 019, it's there. 02, it's not there. Right, so this is pretty precise pinning. We're still at a R squared for like 040. And it's in the top 57. So there's 57 non-zero coefficients, and we can see what they are here. We see most of the personality variables are retained, O, C, E, A, and all ocean factors are actually retained at this level. What about grit? Yeah, so grit is not retained. I guess it's highly collinear with conscientiousness, which is the better representation, it seems. Risk seeking, favor programming career, like these are the things, right? So these are the top 57. So it's in the top 57, but not in the top 51. And what's the sign of it? Let's see, by the way. Gender.male has a negative sign. And that's after holding constant all these other things like personality. So a male and a female, like with a similar personality, the male will tend to be less favorable to alternative credentials, which is kind of interesting, and it runs counter to my original hypothesis, which is interesting. So 57 is what we got, 57 out of 165, right? So it's in the top 35%, cool. 57 out of 135. Is top 35% of factors. Okay, so we did this leave one out cross-validation, and this is with plain gender, and we see that plain gender is in the top 35%. But like the theory is that gender straight up is not very informative, that we want to do things like interact it with risk preference and industrial preference, and that's like far more interesting. So here's leave one out cross validation 4 and leave one out cross validation 5 And you can see it's WX, which means with interactions. And basically the main interaction is this really cool four-way interaction, which we know from the exploratory study is like a big deal. So we go through here and find here, so like the top 3 variables, there's no gender. But when we get to the top 5 variables, now we have one. That's just one. I think that's just one big ass gender variable. You can see when it's a four-way interaction, they get big. And this is, and how interesting is this? That it's men in tech. It's like, of all the industries, it's specifically men in tech. Which is hilarious to me. It's specifically men in tech that have an important, like, top 5. And it's not, remember, so here, this is top, so it's like top 57 out of 135. No, that's not right. 165. 165. Did I do that division correctly? 57, 165. Okay, good. Had 35 on the brain. So here it's like 57 out of 165. Now imagine we made it 5 out of 165. That would be impressive enough. It would be in what, like the top 3%. But here, that's not the case. It's not top 5 out of 165. We've increased the number of variables to 246. So it's top 5 out of 246. So this is an extremely important interactive effect. And if we go from 05 to like increase it by an order of magnitude, and we go to the top 20 variables, now we got 1, 2. No, it's more than that. It's like 1, 2. You can see the commas. 3, 4, 5, 6. So 6. So gender variables. I'm trying to indent this, and like my life is bad. You're making me hit the space key instead of the tab key, really? 1, 2, 3, 4, 5, 6. Yeah? 1, 2, 3, 4, 5, 6. And interesting to note that they're all different industries, yeah? And don't be surprised that they're all male. It's a binary variable, so 0, 1 encoding, 1 is defaulted. So this doesn't mean that like men are the only one with effects. No, what it means is that the female effect is encoded in the default. So the only difference that can be found is among men. So I'm only looking at male and female because I only had 2 samples who said non-binary gender. So that's not enough to do any statistics with, right? So I'm only looking at men and women. I'm not looking at non-binary responses because they're just so rare. If someone wants to give me a huge grant to do a huge study, I'd love to do it. Send me the money. But I'm not going to pay that out of pocket. Like I paid for this samples out of my own pocket. So there's 1 in the top 5 and 6 in the top 21. Right? So if you're like, oh, 1 in the top 5, there's probably like 4 in the top 20. No, there's 6 in the top 21. So it's not like this is like, you might have a couple theories. If you go, oh, there's 1 in the top 5, you might go, that's a lucky one. Like mostly gender doesn't matter except for this one weird interaction. So there's going to be like 1 in the top 5, and there's only still going to be the 1 in the top 20. And you're going to have to go closer to that like 35% mark or even further to get more important effects. It's like, nope, you got a bunch of them. And this is still in the top 10%. So here, it's like top 35% of factors, but here, it's represented in the top 2. It's represented in the top 2%. It's in the top 2% of factors. Single effect in top 2% of factors, which is like maybe spurious, maybe sus. 6 out of 21 in top 21. So I think we can do better than, so 246. It's definitely top 10, but is it more impressive? 9, 9, 10, that's splitting hairs. If you're like top 9% instead of top 10%, you're just like flexing too hard. Hey, Dan Cruz, I appreciate it. Good to see you. So single effect in the top 21%, in the top 2% of factors, strongly represented in top 10% of factors. Cool. So we went looking at straight up gender. It was like in the top 35% of factors, which you might even go, it's like, it's not even that big a deal. It's sort of like moderate. It's moderately important if you look at gender straight up. But if you look at interacted gender, now you're sort of in the elite class, like, okay, we can tell it really matters at this point. And it specifically matters among these industries. So that's interesting. It's like, does gender always matter? Like, no, it matters in these industries specifically. And the number one industry is information technology. Now, is that a coincidence? Actually, no. We have really good theories that predict this. And that's interesting. When you look outside of information technology, I think we can use similar theories that we have to support education, finance, and health. But when it comes to manufacturing and transportation, I am not confident. Like, I don't think I have a theory to explain those. I think at transportation, I would guess that this has to do with like regulations. So transportation is pretty regulated. Like, to be a driver, you have to like pass a certification, right? You have to be like a certified, what is it? CDL, certified driver's license, I think is what a CDL is. Manufacturing, I'm just not familiar with the industry at all, so I can't speak to that at all. But I can tell you health is heavily related to alternative credentials, right? If you're a nurse, if you're this, if you're that, there's like a certification for everything in health, right? So the connection is with certifications. And the point is, this is to do with alternative credentials. So the point is, if you can pass those credentials, like exams, and prove that you have the skills, why do you need to go to college? Like, that's kind of the idea. It's like, if I can code, I shouldn't need a degree. I have the skills. And that's the same for health. Now, there's a bit of a bifurcation here because I think this is agreed to heavily by a lot of like nurses. But when you actually get to like medical doctors, they're like, no, you still need college for MD, but not for like, there's like 1,000 roles in health where you don't need a high level of education. Education itself doesn't really surprise me. I want to see the direction of effect. I would actually maybe kind of expect that to be negative. Let's go see. So analysis 5. So you can see this going either way, but the idea is that people who are in education would certainly have stronger opinions, and I would kind of think that they would want to resist alternative education. So this is gender male favor programming. Let's go see. Gender male favor programming education. Yeah, so the effect is negative, right? So it's significant and it's negative because most people who are professionals in education, most of them are professionals in the public education system. There are more public educational employees than private educational employees. And so you can see the public education system is self-interested, right? So this is the theoretical explanation. This is not talking about people being self-interested, although that's true as well and largely related. But there are systematic incentives that cause the system to be self-interested as well. So when you look across the education industry, and you see that most of the education industry has to do with public education, you would expect those people to basically be defensive, to put it rather bluntly. And you can see this with like teachers unions, for example, like people very much throwing a tantrum at the thought that like parents would be involved in curriculum selection or something like that. So all of the opposition to school choice relates here. And then finance, I'm expecting positive. Yeah, positive. And it's the similar idea. If you have the skills, like why not? Why can't you do it? So these are largely positive. $187. Okay, this is this ran with the super small L ratio. And you can see at this level, most factors are retained. So that's kind of the naive question. Like, is it important? Well, is it even in the top half of variables? That's sort of the naive question. And it's like, yeah, definitely is. So that's stuff that I've done offline. Let me check in those notes and then we'll talk about what we're doing today. Basically, we want to robustness check these results. So this is elastic net leave one out cross validation with and without interaction effects. But we want to robustness test those. Like, we don't want to only be using elastic net. Elastic net is really cool because it's a hybrid of lasso and ridge regression. So it's like almost robust by itself. You get some of the benefits of lasso where you're dropping unimportant factors and keeping important factors. But you're selecting those in a stable way, unlike the pure lasso, which is an unstable selector. We talked about that earlier. So the feature, oh man, I don't know why VS Code jumps me around like that sometimes. So the feature here is like more precise identification, elastic net percentile identification. Elastic net percentile identify. What you see, it like jumped me down there. I don't know why. Something like when the memory is like too busy, it just starts geeking. It's really confusing me. Okay, so we've done all this elastic net stuff. Woo, cool. Now, today, I want to do a completely different feature selection approach. And so we have these four. One is called generic univariate selection, which just means testing factors one by one. That's what it means, testing factors one by one. So when we did the elastic net, we're putting in a multivariate regression, like multiple independent variables. And we're shrinking those coefficients. And if you shrink them enough, at some point they become unimportant and they drop out. So that is the elastic net approach, basically. With generic univariate select, it's going through all of your independent variables one at a time. And it's checking that regression and that regression and that regression. Now we know, because from our exploratory analysis, we know that gender by itself is weak in a univariate regression. We know that. There is not a statistically significant difference between men and women on favorability of alternative credentials. If you just look at that factor, it's not statistically significant. So we know that. That being said, we can still get a percentile rank of importance because even though it's not significant, there's a bunch of factors that are not significant. And it might still be more significant than like some of them, which it is. So these will give us, and there's two ways of doing this. One is FDR, which means false something rate. False something rate. What is FDR? It's like false rejection rate. FDR versus FWE. Expected proportion of the null hypotheses that are falsely rejected by the total number of rejections. False discovery rate, yeah. And it's basically, it's the less strict of the two. So FDR is like, so 0.5 is my threshold here, which if I'm using that with FDR, here's the translation. Of all the factors that I select and keep, most of them are not false selections. Most of them are not false selections because it's going to limit it up to 0.5 statistically. So we expect that most of them are not false selections. That's the idea there. And that so you can see like individually, A, B, like A, what's the percent chance that it's right? 0.49. B, what's the percent chance that it's right? 0.46. They're all individually under 0.5 at the p-value. Does that make sense? Yeah, so I got these wrong. I've expected proportion. And then FWE is a cumulative test. So it's like A, B, and C. We are more than 50% confident that A, B, and C are all good selections. So it's a cumulative test. That's the difference there. So the cumulative test is more strict. And like I already ran this, but basically I think the cumulative test gives me 8 results and the non-cumulative is like somewhere in the 10s or 20s. Keep best proportion where false discovery under 0.5. Where false discovery, like proportion is under 0.5. Cool. And then what I wanted to do was the RFECV, recursive, how to start coding. Hey, so I would recommend you start with web development, like JavaScript. So I'll give you 3 specific places you can go. One is laterally.io. So you can register here and join the Discord. Encourage you to do this. This is mine. Like I created this. Another place that you can go is Free Code Camp. The good thing about Free Code Camp is it's free. Some of the curriculum is a bit dated, but some of it's pretty good. Sean Wang is pretty cool. Swix. So that's Free Code Camp. And Codecademy is where I learned myself how to code. So this is the one I recommend most of all, but it's not free. But if you're kind of like self-driven and if you can keep yourself on track, just do this front-end engineer career path, and that will get you job ready. Xbot Freak joined. What's up? Thanks for joining. Rockaway says, what are you doing now? Yeah, so I am doing data analysis right now. So here's the code. This is in Python. So I would not recommend that you like start with, if you've never coded before, I would not recommend that you just like start doing this. This is pretty complicated. You can actually like hurt people if you just start doing statistics and machine learning, and if you have no like theoretical understanding of what you're doing. You can misinterpret results and mislead business decisions and cause bias to occur at your company and end up hurting people. So please, 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 like, don't just dive in and start doing machine learning and not really understand what you're doing at a theoretical level. That being said, I have a PhD in economics and I've been studying this topic for a long time. So the question here, one way to phrase this that's pretty concise, is that computer science college programs are 20% female and programming boot camps are 40% female. Why? So we're trying to understand why. And when we find out why, maybe that explanation is instrumentable. So some explanations are sort of brute facts. It's like it's true, but you can't do much about it or with it. Other explanations lead to instrumentation and levers that we can use to manipulate the world around us in a causal way. So causal analysis is like at the end, you want to do like inferential and like theory testing and do your causal analysis like at the end. So we haven't gotten there, but if there turns out to be a difference, and basically there has turned out to be a difference, several of them, then it's like maybe we can do something with that information to increase diversity in tech, which is kind of the one of the main motivations for doing this work. Okay, cool. So we did the false discovery rate, generic univariate selection, and the family-wise error, which is the cumulative, right? Generic univariate select. So these are two very different approaches compared to the elastic net, where you loop through the factors one by one and doing simple regressions. Then there is this approach, which is RFECV, which is recursive feature elimination with cross-validation. I'm a huge fan of this, but we can't use it. So I don't have enough samples. So with recursive factor elimination, you need to have more samples than independent variables. And I can't do that. So that brings us finally, after this like super ridiculously long-winded intro, to the thing that we're doing today, which is we are going to do forward selection instead of recursive feature elimination. We're going to do recursive forward selection. Recursive forward selection is a second best approach. Like, it's not regarded as a good approach, but it's appropriate to use here because I have more independent variables than samples. Bro, what that name? Hey, thanks for dropping in. I'm doing some stats right now. Appreciate the likes. By the way, this is just what I'm working on right now, but if y'all have other questions, like, hey, you know, I'm trying to code X, Y, or Z, like, you can drop whatever questions you have. Like, feel free. But if I'm not, so like if I see a question, I'll try to address it. But if I'm not seeing a question, this is what I'm working on currently. J, how do I say this? I don't know. J Sauce, whatever. We'll call you J Sauce. Thanks for joining. So we're going to do forward selection. So let's do it. So this is just something that I Googled. How'd I find it? I literally, look, I'm not that creative, y'all. Python forward selection. And I also know there's recursive feature elimination here in sklearn. Maybe there's something about forward. I think it's sequential feature selector, maybe. Yeah, so I'm not seeing like, so here's like RFE, recursive feature elimination. I'm not seeing like RFS, recursive forward selection. I don't really see that. What I do see is this one. Maybe I can look for the word recursive. Yeah, the only built-in recursive approaches that I even see are those. So like the first place I just checked is the docs, but I couldn't see it. So then I just Google Python forward selection. And we'll look at a few of these. Okay. Does Scikit-learn have forward selection or stepwise regression? No. Scikit-learn deliberately avoids inferential approach to model learning. So stats model, yep, stats model uses inferential learning. So maybe we'll do stats model. Oh, a scikit-learn compatible ML extend package supports this approach for any estimator or metric. Okay, so this guy, like, whoa, I appreciate this guy, David Dale. David Dale, like, open sourced this stepwise selection. That's wild. It's like right here. It does have a forward selection algorithm. Will sequentially include features that improve the model the most until there are K features. It starts by regression, the labels on each feature individually, and then observing which feature improved the model the most using the F statistic. I'm okay with that. So there's different, so whenever you do one of these stepwise regressions, you need a criteria, like a selection criteria. Or you can use AIC, BIC, adjusted R squared, whatever. F regression, I'm fine with that because basically the F statistic, it's a measure of your model power. So I'm fine with that. Let's see this announcement. A new iterative transformation can add features one at a time based on a cross-validated score maximization. That's cool. Allow in features to select to be an upper limit in sequential feature selector. Whoa. This is really cool. This is really cool. I'm loving it. Feels cutting edge. Looks like you merged it to main 10 days ago and it passed tests, but there's a conflict. No! All right, cool. Well, we can look forward to that coming soon. Neighbors classifier. So I'm not going to use that, but that's cool for like the soon future. Check out F regression. And then this guy uses stats model. Univariate linear regression tests returning F statistic and p-values. Cross correlation between each regressor and the target is computed. It is converted to an F-score and then to a p-value. Univariate linear regression tests returning F statistic and p-values. Univariate linear regression. Yeah, so it's testing the x's one by one. So does have forward selection algorithm, although it isn't called that. The feature selection method is called F regression, and Scikit learn will sequentially include features that improve the model the most. Starts by regression, it should say regressing labels on each feature individually and then observing which feature improved the model the most. Then it incorporates the winning feature into the model. Then it iterates through the remaining features. Notice that the remaining features that are correlated to features will probably not be selected since they do not correlate with the residuals. Yeah, that is totally fine. That's like a good thing. That's like the whole point of doing this, is to partial out collinearity. So the only problem is I don't see it doing what this person said it does. This is not a stepwise selection because each p-value is calculated for a univariate regression independently of all the covariates. Right. You get a downvote, dude. Oh, I can't downvote you. That's sort of forward selection, but it's not generic. It is specific to a linear regression model. Yep. Hey, what's up, Luca? Yeah, sklearn and maybe stats model. Trying to figure that out right now. Scikit-learn and maybe stats model. Kind of feels like a lot of the people talking about these things don't actually know what they do. What's the goal here? Doing gender research. So I'm presenting at a conference next month. So about 20% of computer science programs are female, 20% of students. And for coding bootcamps, it's about 40%. So why is there a difference? And is there anything we can learn from that to potentially increase diversity in tech? Yeah, so I don't think Scikit-learn is going to give us a stepwise regression. So I think we're going to have to implement our own, which is totally fine. So this guy literally wrote us stepwise selection, which is pretty cool. So I might use this one, or I might not, because I have a few other articles. So let's check it out. Wrapper methods in Python. Analytics Vidya. Why stepwise regression? So just because it's another route, we're not only using stepwise. So I started with Elastic Net. Another reason to do stepwise is that this is a meta-analysis, and some of the studies in the analysis used stepwise. That's another reason to do it. Yeah, so I think the big question is like, compared to what? Like, why not stepwise? So one of the main motivations for using backward feature elimination is that we can go by p-value at the feature level. And the p-value, so we're doing hypothesis testing, feature level hypothesis testing, specifically the gender independent variable and its interactions. And the p-value will tell you whether or not, or like what % likelihood we expect that to be basically accurate, different from 0. So if you can get a p-value that's less than 0.5, then what you're saying is it is more likely than not to be different from 0, basically. Or another way you can say that is like, we expect this to be a true effect. We expect this effect to actually exist. So that's a reason that the p-value is important. And then the question becomes, well, how do you use your knowledge about the p-value to optimize a model? And stepwise selection is a really straightforward way of doing that. You just um, iteration by iteration eliminate the highest p-value factor, and then you can reduce your model to a model where all the factors are 0.5 or less. So that's backwards elimination, which is a little better than what I'm doing. I'm doing forward selection. Why am I doing forward selection? Because I have more independent variables than samples. That's the reason. Good question, though. This guy's doing random forest with a test train split, so that's not going to work for me. Sequential feature selector from ML extend, except that we already have sequential feature selector from sklearn. Linear regression, cool. So here's forward true. Okay, so this is what we're actually getting, SFS. Okay. Didn't know you could get good results on D greater than N. Yeah, I'm not actually familiar with the notation of D. Usually we call it K or P, but cool if you're calling it D. And good results, you can, yeah. So the real way you do that is called an elastic net, or the broader pattern is called a shrinkage pattern, or penalty modeling. Sometimes it's called penalty modeling. So like that would include lasso regression, ridge regression, and elastic net, which is a hybrid of those two. So that's like the best way to do that. Yeah. Cool, so this seems pretty straightforward. So let's just blindly do it and see if it works. ML extend, cool, fine, I don't know. So let's close to the right and import sequential feature selector as SFS. Need to install this guy. And then let me go to my requirements file and specify, I guess, can I just freeze again and see what happens? Oh, I need to echo to file. Hey, see you later, Luca. Thanks for dropping by. It was good to see you. Cool, so that just added ML extend. So we'll chore that. Chore ML extend. Username user1 joined. What's up? Thanks for joining. So this is still not detecting ML extend, although we did install it. Why would that be the case? Let's look in the PyCache folder. That's not helpful. Can I just do that? So it's saying ML extend is not even there, but it definitely is. Franzy Pants, what up, what up? Cool name. What are y'all watching on Netflix these days? I just finished You, the new season. That was pretty crazy. I'm going to, let's see, undo this. Bam. Grab this. Save. Close my file. Close this. Get ready. Close VS Code. Cocaine Bear. Liddy. If that's not a lit name, I don't know what is. What's up, Cocaine Bear? I'm tired, y'all. What's this extension? There's a extension. I think, honestly, I just think my memory is getting maxed. Let me check my performance here. Yeah, 100% CPU. Yeah. So I think that is the real reason. That it's like, oh, you haven't installed this yet. And I'm like, yeah, I did. I think the computer just hasn't caught up with itself. Control S. See, I'm not getting the yellow issue this time. And that should go down. Yeah, okay, it's going back down, right? Like VS Code has to load up and it's kind of a hog. But after it loads up, it's like pretty much fine, I think, yeah. Maybe I should get a new CPU. I don't know. Coolio. Math is great and statistics is fun. Woo! SFS. I need some nicotine. Linear regression. I think I already have linear regression in this context. Yeah, boy. And an SVR model. That's kind of crazy. Did I use? Oh, yeah, we're going to do an SVR model too. Just put your seat belts on your bodies. Nerds. Cool. So this is going to be, we can still call it model LR and model SVR. We can still use those names. It's fine. Linear regression and SVR scaled vector regression, some kind of vector regression. Cool. Neg means squared error. I don't want to do that. Let's see what are my scoring options. ML extend. Let's check out the docs. I want to go by adjusted R squared if possible. Whew. Oh, it's going to tell me right here. That's convenient. So scoring default is none. Scoring. Uses accuracy and R2. I'm not sure how accuracy is computed. Mean absolute, mean squared error, neg, mean squared error, median absolute error, R2. Those are what? Uses sklearn scoring metric identifiers. If string uses, okay. Precision recall ROC-AUC. I don't know what that is. ROC-AUC. So the mean squared error thing, that's useful for like prediction, basically, and I really don't have a predictive use case. I'm trying to do inference here. So I would like to do adjusted R squared, not R squared. Let's see, what happens if I just do R squared? Will it not just like keep all the, it'll just like keep all the variables, won't it? Except like at the end, the ones that are like perfectly collinear, it'll ignore. And I want to exclude more than that. If a callable object or function is provided, it has to conform to sklearn's signature scorer. Okay, so I can calculate the adjusted R squared. Maybe I have my own scorer function. Okay, something here is not working. Linear regression. Here is the linear regression, and then here is the SVR regression. K features. I don't want to specify K features. I want you to optimize for me. Forward is true, sure. Verbose 2, I guess. Yeah, it would be nice if I could do cross-validation. There's not going to be any cross-validation. That's the whole point of going this way. Mean squared error. I guess I'll do top 10%. So So 25. Spectacular join. What's up? So the only thing I'm concerned about is the negative mean squared error here. Okay, so that's fine. So I'm wanting to do inference, and I'm wanting to do within my own data set, but scikit-learn is providing me predictive measures, not inferential measures. So fine, let's treat this as if it were a prediction problem. And if it were a prediction problem, why would I prefer negative mean squared error? Right, this is where I saw the others. Uses a scikit-learn scoring metric string identifier, for example, accuracy F1, precision recall. I'm just going to copy this whole thing. And I'm not going to do a custom function. Oh, there is a CV in here? What? CV default 5. So I will pass it a CV. It'll be a leave one out CV again. Cool, so I did leave one out right there. Cool. And then here is so negative mean squared error versus mean squared error. Yeah, why would I want negative mean squared error instead of mean squared error? I don't get it. Let's do mean absolute error versus mean squared error. there's the mean absolute error, and then what was the median? Median absolute error. I think I just leave it alone, and if someone's like, why? I'll be like, because this guy, and just like cite it. That's fine. Okay, so there is the model LR. Here is, we are now getting results LR. It's just model LR fit my data. And then let's go see what it does. Hey, so I kind of prepared this, although it never worked. So LR get support. I don't know if that's a thing. It'd just be K feature names. Cool. So we just go K feature names. So column names are results.lr.kFeatureNames. Much simpler. And then we get the gender ones and say LR, LR, LR. That's all looking good to me. LR column names. Very cool. Cool. So it found the collinear features. That's great. Drop them. I don't want them. Invalid value entered in true divide. What? That is not something that I like to see. I wonder if I kill this will I ruin the things. Oh no, I think that's fine. It's just because it's a 0 there. Cool. This is kind of slow, isn't it? But that's how it'd be. So what are y'all up to? Let's see if I got any questions in the. Oh, Sir Dies a Lot says hello. What's up? Sir Dies a Lot, cool name. Cruz Sama, how's it going? I guess word to the wise, this is like kind of a slow approach, isn't it? But it's getting done. So we've got 5 done. Is that 5 done, or we're on the 5th one? Dave Bullcock, what's up? So we're going to try and get these results. I wonder how I can increase the parallel jobs. You know what? I don't know if I should increase the parallel jobs, right? Because it's supposed to be stepwise. Yo! You totally should. Oof. I don't know if troll or not. Sid Coop. What's up? What's up? I feel like I need like a better computer because this is so slow. All right, so it's going to go through and find the top 25 features. Yay. Then we're going to want to repeat it for the SVR, and that's really kind of the whole thing. As long as it doesn't fucking crash and kill me. So I won't put y'all through this twice. When the first one is done, like again, assuming there's no like errors that I gotta fix or anything, I think we just call that a stream for the day or evening or whatever. Oi. So there's the score. We can see the score is getting closer and closer to 0, which is a good thing, because that is the error, basically. Negative mean squared error. So the closer it is to 0, the less error there is. So when this analysis is done, we will basically have the main factor level insights into credential favorability, which is cool, but you can see on the left here, analysis 7 logit could arguably be even more useful. And that'll be the final thing that I do before I just like straight up write up the paper and I'm kind of done. So the logit is going to have a different dependent variable, a different y output variable. So currently the dependent variable is credential favorability. Yeah, and what did I have in the logit? Let's see. Is tech, was that what I was going to do? Is tech. Yeah. It dawns on me that there's like a third thing to analyze, although I don't know if I'm going to go into it. But the third thing to analyze is if you would enjoy a career in programming. This one. So I guess the first thing to study is tech, because what we want to prove is that, this sounds like super obvious, right? But we want to prove it first. What we want to prove is that if you favor a career in programming, you're more likely to have a career in programming. Because it could be the case, right, that like the people who are in tech are like, fuck tech. Like, that's possible. But I'm doubtful of that, in particular based on my own experience. but it's definitely something to validate. You don't want to make an assumption. So this logit will validate is tech, and then the idea is that this is going to be an important factor of is tech. And then maybe, or maybe it's a separate study, want to analyze that guy, because we're kind of just begging the question, right? There's two. I fucking hate it, right? Research is never ending. Maybe I should be happy and put a smile on. Like, research is never ending and it's kind of beautiful. But so much of our answers just beg new questions. Two begged questions. I think that's scope for another study. So I'll make a note in my conclusion. I'll make a note there. I'm not going to try to answer those. Yeah. All right, so we're on 23 out of 25. We're getting there. And the score is under 0.5 now, which is a good thing, which means at this point, and this is the squared, right? This is squared. Hold on, let me double check that. Negative mean squared error. Yeah, it just means we're, I think this means we're getting a lot of shit right, basically. Okay. So LR result length is 25, includes zero gender variables. Oof, but at least it didn't err. So I feel good about that. All right, y'all. Well, thanks for tuning in. That's going to wrap up the stream. Basically, I have to run this a few more times. So it's on 25. I'm going to go for the 35% threshold. But I won't make y'all stick around for that. And then I'm also going to run it for the SVR, which is just going to take fucking even longer. Cool. Thanks for tuning in. Talk to you later. Bye.